Okay, welcome back. In this video, we are going to talk about the classical average value theorem. So this is another math interlude. This is really kind of mentioned in chapter 1.3 in your textbook, but not super thoroughly explained. And it turns out that this is a concept that is going to be used a lot, both this semester and next semester. And so I wanted to make sure that we talked about what this means so that we have the skill set moving forward. Okay, so remember when we started talking about the kinetic molecular theory and Boltzmann distributions, we started from this idea of the Gaussian distribution. And we said this was for things that are random. Well, the Gaussian distribution is very nice because it is symmetrical. And when we have a symmetrical distribution, the average value is the middle of the distribution, or the peak. And so if we were thinking about person height, we have extremely short people on this side, extremely tall people on this side, and we have an average height. Now, a lot of distributions that we work with are not symmetrical, so determining the average value is going to take a little more work. And to do this, we are going to have to use the idea known as a weighted average. Okay, so the normal average that we've done in all of our classes is really assuming that we have a normal distribution, that everything that we're measuring is random. So if we were to do multiple trials of density and we wanted to find the average, remember that our average is going to be the sum of each of the densities that we determined from our experiment. 0.955 divided by the number of measurements that we took. So we can write this out in a compact form as the average is the sum of the individual measurements divided by the total number of measurements. This is how you find the average if you have a normal distribution. And so that means that in this case, the error that is involved is random. So if our measurements are completely random and so this distribution is symmetrical, then we can find the average this way. Basically, what this means is that the probability of finding each of these values is the same. Normal average. Now, the general form of the average is not going to work if our distribution is not symmetrical. Is not going to work if our distribution is not symmetrical. And so then we have to think about a better definition of how to find the average. So in the previous equation, we are assuming that the probability of each value appearing is the same. And this means that it's a symmetrical distribution. In the Maxwell-Boltzmann distribution, the probability of each speed appearing is not the same. That's why this distribution is not symmetrical. Notice how on this side we have a long tail, especially noticed in this blue curve. And so the average velocity is going to be calculated by the classical average value theorem. Sometimes we call these expectation values. So we're talking about the value that we would expect to show up the most often, or the average. And this is sort of a weighted average. And to do this, what we're going to do is we're going to take the integral of the function that we want to find the average of times the probability of the distribution. So for the Maxwell-Boltzmann distribution, what we would end up doing is if we want to find the average velocity, which in our textbook we're going to denote with these brackets. We are going to take the integral of the velocity times the probability of the velocity, dv. And normally what we need to do is we need to do this over all space, so from negative infinity to positive infinity. Okay, so when we define our average in this way, we no longer just have to find the average of our x-axis. Instead, we can find the average of any function that we want as long as we have a probability distribution describing that function. So if we are thinking about our Boltzmann distribution, we showed earlier that we can find the probability of the velocity by integrating over all velocities with the velocity times the probability of the velocity. Well, what if I wanted to find, say, for some reason, 1 over the velocity? I could, because this is I would just integrate from negative infinity to infinity of 1 over the velocity times the probability of the velocity. Okay? In physical chemist, we like to find these expectation values or these averages of a lot of these different functions, and we use this bracket notation around the term to indicate that it is the average value. So this is the average. Okay. Generally, the integration limits cover the full range of values that the x-axis could exhibit. So in reality, I could say that my velocity is never going to be negative, and so I wouldn't have to start at negative infinity. I could start at 0. Okay, so your now try this problem is that molecular motion is often described in terms of the mean squared speeds. This comes from convenience of relating the motion of molecules to kinetic energy. Provide an expression to calculate the mean squared speed or velocity of a sample of oxygen gas at 300 Kelvin. You should add any constants into the expression, but you do not need to simplify or solve the integral expression. Okay, this is the end of chapter 1, and the next video that I post is going to start us off into chapter 2, really starting to dive into what is statistical mechanics.